So, welcome back to part 3 of this series. Behind me here you see the electrical system of my Queen Bee Pro CNC, and here to my right you see 4 absolutely vital components of this machine. They are the stepper motor drives for the X, dual Y and C axis of the machine. And without them it would be absolutely impossible for my computer to control the movements of this CNC. And why that is, I'm going to tell you now. So in the last video we talked about motors. But even though they are extremely useful in many situations, motors by themselves are quite useless. I mean, sure, a DC motor, you can add a battery or a switch and you can run it. But it will only run at one speed and one direction, unless you turn the battery over. And stepper motors or servos, they won't run at all. If I simply put a battery on one of the windings, the rotor would lock up and stay in one position, and that's not really what a motor is meant to do. So what do we need to tell a motor to go in a certain direction or at a certain speed or velocity or even to a certain position? Well, we need a driver. This is probably the simplest driver there is, apart from an on-off switch. This is a small circuit board I designed that generates a PWM signal. Now, PWM stands for pulse width modulation, and that's a fancy way of simulating an analog voltage using digital signals. Now, this entire circuit board is based around a 555 timer. Now, if you want me to go into depth about pulse width modulation and this circuit board, I have another video about the board that will be linked down below, and if you want me to explain pulse width modulation more thoroughly, leave it down in the comments. But simply put, the timer pulses this power MOSFET on and off, varies the time it stays on, and this variable on time gives a simulated analog voltage on the output, or a variable voltage on the output. And this is extremely useful for driving DC motors, or like my home-built LED panel over here. But this circuit will only give me control of the speed of the motor, not the velocity, the torque, the direction, or the position. And that is because this PWM signal is built around the timer IC. And the time between the on pulses and the off pulses for the MOSFET is controlled with a small potentiometer. Now, if I wanted control over velocity, direction and speed, what I would need to do is replace this timer with a microcontroller, or a small computer basically. Something like this. This is an Arduino Pro Micro, and this is a small 8-bit microcontroller. Now, by writing code for this microcontroller, I could tell the pulsed signal going to the MOSFET exactly what I want to do. And if I have an H-bridge hooked up, I could also change the direction of the polarity and make the motor spin the other way. But all of that would be done in software. So what can we say so far? Well, a driver is a way to interface the brain, or the computer or controller, or whatever you want to call it, with the motor. Because this one only outputs a voltage of 3.3 or 5 volts, and that's not nearly enough to drive the motor. We need an intermediary step that both can listen to the control signals from the computer or microprocessor and also be powerful enough to drive the motor. So let's move on to more complicated drivers. These two are the same thing. Or, well, obviously they're not the same thing, but they are both stepper motor drivers. And we interface with them both in exactly the same way. Only this one is through a terminal block and this one is through the individual pins that are breaking out from the small stepper driver IC on here. Now, stepper driver comes in all shapes and sizes. These two are two of the most common for hobbyists. This is a clone of a Toshiba TB6600 drive. And if you get an original one, or a good copy, they are okay, but the more modern digital DM542 drivers that I have on the Queen Bee Pro CNC are a lot better and higher quality and easier to use as well. These ones suffer from quite a bit of issues, and if you want to know more about that, just Google it. So what does this driver do exactly? Well, of course it interfaces with the motor. That's done through this lower terminal right here. We have the A winding and the B winding of the motor. We have the high voltage / current input, which is the VCC and ground. And that can be anywhere between 9 to 42 volts DC on this model. Some other models go up all the way up to 56 volts. And generally you want to run drivers with a voltage in the higher range. So my drivers in the Queen Bee Pro go up to 42 volts. I run them on 36 volts because that was the power supply with the closest voltage I could find. And you want to do that because the drivers become more efficient at higher voltages and in turn run at lower current. Now, how do we interface this one with a microcontroller or a CNC controller? Now, you interface with almost all of these hobby drivers using something called pulse train signals or pulse train output. And here you can see the two inputs, the pulse input and the direction input. Now, the direction input, of course, as it implies, tells the motor which direction to spin. So if you, for example, put 5 volts across the direction pins, it goes clockwise. If you pull it to ground, it goes counterclockwise. And the pulse input tells it how far to move. So in its lowest setting, which is without any microstepping, 200 pulses on this input will tell the motor to move 1 complete revolution. At least if it's a stepper motor designed for 200 steps per full rotation. You also have some settings on this, and the two most common ones are the microstep settings and the current settings. So here we have the legend on how to set these dip switches for the different modes. Now, dip switch S3, S5 and S6 are used to set the current from 0.5 amps to 3.5 amps with a peak current of 4 amps. And for that setting, both S4, S5 and S6 are supposed to be turned off. As they are, since you can see that on is downward. And for the microstep setting, we can choose between all the way from 1 to 32 microsteps, which means that for each full revolution of the motor, we need to pulse the input 6,400 times. And this driver is currently set for 16 microsteps, which means 3,200 pulses per full revolution. And this driver have exactly the same settings as this one. The only difference is that this driver can drive up to 4 or 5 amps, and this one can drive up to 2.5 amps. These are more commonly used for 3D printers or really small hobby CNC machines. Now, on some of these drivers, mainly the ones in my Queen Bee Pro CNC, the DM542 ones or the DM series, you also have a holding current setting, which means that at rest, you can tell the motor to be energized either at half current or full current, to tell it how much power to feed into the motor to keep the output shaft static. Now, more advanced stepper motor drivers also have inputs for encoders, and they can communicate either serially through USB or RS485 or 232, or over Ethernet, or over IO-Link, or a whole bunch of different communication protocols. Now, these aren't that often used for hobbyists, but within industry, definitely. And if you want the most bang for the buck stepper motor driver you can get that would be excellent for a home hobby CNC machine, I would urge you to check out the Festo CMMO DIO driver. It can drive up towards 5 amps and you have full control of everything. You can basically turn your stepper motor into a servo using that driver. This driver is cheap. This driver I have here probably costs around, I don't know, 25 euros, 30 euros. I'll leave something in the screen here somewhere. But one of the Festo drivers costs up towards of 400 euros. So that's a trade-off. So let's move on to a more advanced type of driver. Now, I showed you this in the last video and I told you it's a servo motor, and it is. But it's a servo motor with an integrated servo driver. Let me show you real quick. Now, here you can see something that is basically a brushless DC motor, used in like RC planes and stuff. But what's really cool here is this board. And this is the integrated servo driver board. Now, I think I told you in the last video that the main difference between a stepper motor and a servo motor is feedback. And what that basically means is that if I tell the stepper motor to move 200 steps, I have no idea to actually know if it has moved 200 steps or 192. Now, in a servo motor, if I tell this motor to go a full revolution, I have a feedback signal. Or to be more precise, there is a feedback signal to the driver telling the driver or the microcontroller on this board exactly how many degrees or how many steps or how far it has rotated. And that makes all the difference. Now, the feedback can happen in a couple of different ways. One of the most common ones is through pulse encoders, which I will talk about later. On older CNC machines with DC servos, we have glass scales. or magnetic scales, and that is exactly the same type of scale that you have for your digital readout for a lathe or a mill, for example. Now in this particular driver, I'm not actually sure what the feedback is. I know there's a feedback, but the technical specification from the supplier, Simplex Motion, doesn't say exactly how it's done, but I suspect we have internal Hall effect sensors in this motor. And Hall effect sensors read a magnetic field. And by reading the magnetic field that is created by the coils and by the rotor rotating, we get a feedback signal telling the brain box the position of the rotor. Now there are of course both DC and AC versions. This is a DC servo, or to be more precise, this is a brushless DC motor. You can also have brushed DC servos. That's really common on older CNC machines. And what's typically done on brushed DC motors is that you tell the motor to move at a certain speed and a certain direction, and then you read the feedback from the glass scale, and then the motor of course is ramped up or ramped down depending on how close to the final position it is. Now the driver boards are not that often integrated, only in the smaller motors like these Simplex Motion, or we have some lead shine servos or clear path servos with integrated motors, and they are excellent for small machines and lightweight machines. But usually you have an external servo driver. And if you open the cupboard to a real industrial CNC machine, the servo drivers will probably be the biggest thing in there. Now, how do we interface with servo motors? Well, you can interface them in the same way that we do with stepper motor drivers. This general purpose input-output can be configured to take pulse and direction signals as well, and this motor is configured for that. But I can also choose to communicate with it serially over RS485 or over USB. And some drivers, not this one in particular, you can also talk over Modbus or Ethernet or different types of field buses, or even optically. But if you're using any of those types of drivers for your hobby CNC, you have a lot more money than I have. So what more types of drivers are there? Well, one of the most common ones that you'll probably want to run on your CNC machine at some point is this, a variable frequency drive. And this is used to drive AC induction motors. And these are some of the most common and useful drivers in industry. They come in many different shapes and forms. This is a cheap Chinese 4 kilowatt driver. Now, a common way to explain how a variable frequency drive works is that it chops up the current. And while it might be useful for creating a visual image of how it works, that's not really what it does. So let me just give you a quick explanation of how it actually works. In VFD we have an input step. And on the input step we have the incoming AC line and the neutral. Now after the input step, we have a rectifier. And the rectifier turns the AC into DC voltage. And that means we have a positive and a negative line. Now there's quite a bit of filtration and stuff going on here, but simply put, we feed the positive DC power into a big transistor or a MOSFET. And this MOSFET is turned off and on by, you guessed it, a CPU or a microcontroller. And by pulsing this input on and off, on and off, on and off, we can basically give a PWM signal on the output, which we then use to simulate an AC frequency. Now, while the PWM in this case is used to drive a DC motor or a DC circuit, we only work on the positive side of the DC wave. But in this case, we also work on the negative side. And to work on the negative side, we of course also need to turn off and on the negative rail. And on the output here, we get a signal looking something like this. Now, unfortunately, I didn't have time to build this to scale or paint it, but if we were to hook up a big capacitor to this output, we would have a simulated sinus wave with a controllable frequency. And the frequency, of course, is the time it takes from the signal to go from here all over to here, back to 0. And if we vary the time we turn off and on these outputs, we then of course can create any frequency we want on the output. And that frequency is what controls the speed of rotation of the AC induction motor. There are quite a bit more going into this entire system, but simply put, this is how a VFD works. So what are the main differences between this cheap Chinese version and the more expensive ABB or Allen Bradley frequency converters? Well, for one thing, you have a bunch more settings on the more expensive one. Now, this is the instruction manual for this VFD. And this is the entire instruction manual. It is a total of, let's see here, 23 pages. Now, not too long ago, I had to actually figure out how to run and then also commission and operate an ABB frequency converter at work. That manual was 386 pages long. 386 pages is quite a bit longer than 23. So this driver have a total of 35 settings. There might be one or two left out here as well, but anyway, it says 35 here. Now, the ABB frequency converter I was working with had several hundred settings, and you can also upload different macros to it, telling the driver how to run. If it were to run under velocity control or torque control, or in a pump configuration, or if you want a temperature feedback to it, or using the internal PI regulators, or a whole bunch of other things. And apart from that, the more expensive ones are also a lot kinder to the electrical grid. These cheap ones, I would expect, I haven't checked this, so don't take my word for it, but I would expect that they impart some quite nasty distortions on the incoming power line, and also on the outgoing side probably. The more expensive ones have filters and other circuits in place to prevent that. And you also, of course, have a lot more options for input-output. Here we have 16 inputs, and some of them are dedicated for certain functions. On the more expensive ones, we have expandable input-output racks. And you can also hook up Modbus modules or Ethernet modules, or a whole bunch of other extra electronics to give it more functionality. Now, like with the servo drivers, the more expensive stepper motor drivers, you can communicate with these ones using either serial protocols like RS485 or Modbus Fieldbus standards, or if you're using a more modern solution, I would suggest you use Ethernet, such as Allen Bradley's Ethernet IP or Siemens Profinet. But the most common way of controlling them are probably still using analog signals, either 0 to 10 volt signals or 4 to 20 milliamp signals. And that means that on these inputs here, we have 5 volt in and 10 volt in. If I hook up a potentiometer here and give it between 0 and 5 volts, I will control the output speed depending on the max and minimum speeds I set in the controller. And the same, of course, with the milliamp input. You also have forward and reverse bits. So give a positive voltage here, it goes forward. Positive voltage here, it goes backwards. You have some configurable output and input signals depending on what you want to do. So here we have a jog signal. Put that one high and push forward and the machine will jog. And some of these are, like I said, configurable depending on the settings in the controller. Now, a common way in older systems and some simpler newer ones is actually to input the speed you want the motor to run at in the controller as well. And then simply give it a start signal. So if you put one of these inputs high, the motor will spin in a pre-configured direction and speed. Now, I am planning to show you how to configure and hook up this driver at some point. Not in this video though, since I've already talked for way longer than I thought. And that video will probably be done when I install this on my CNC machine. This is a 2 kilowatt water-cooled CNC spindle. And I imagine the Queen Bee Pro will probably fly using this one. So I hope you like this video as well, and And if you did, you know what to do. All my links and everything are down in the description as usual. And till next time.